typically we draw these nice little triangular prisms. They don't have to be. It's just a material that's going to slow down the light as it passes through. So we take a single, let me get rid of that, take a single ray of light that comes in here, and that light is actually made up of lots of different colors. You've all seen rainbows, I believe. You're familiar with the fact that white light is made up of a bunch of different colors. When we send that light that's made up of a bunch of different colors into this new medium, it turns a corner. It bends. And because they travel at slightly different speeds, they split apart. And so we get, let's see, the red, orange, the greens, and I'm not drawing these with, fantastically realistic colors, because I don't really have fantastically realistic colors, the blues, and we get some things down on that violet spectrum. They split apart, and we see different lines. Each one of these different color lines represents a different frequency. Okay, so let's back up a step. What's frequency? Pretty good. It's the number of times per second or per minute that something occurs. So when we're talking about a wave, the frequency, I don't know what's happening out there, would be the number of times per second that a crest passes this point. The number of times a wave hits this point, that's frequency. And for any wave, for a wave in the ocean, for a light wave, for a wave of electromagnetic radiation, we can describe this relationship. C, now this is speed of light, is equal to lambda v. Oh boy, lambda, Greek letters. V is frequency. Okay. Lambda is wavelength. So for any wave, and each one of these, and my husband makes fun of me because once a year I have my wavelength at the top and bottom of the spectrum memorized. The rest of the year it's completely superfluous information. Nobody needs to know it. I'm never going to ask you to, seriously memorize that because really, nobody needs to. Unless you're going to be a physicist who's working with light. Okay, so violet end of the spectrum is about 400 nanometers. Okay, I had that roughly in brain. Red end of the spectrum is about 700 nanometers. These are some pretty little waves. And remember, wavelength is measuring crest to crest or trough to trough. That's a wavelength. Okay. So what are we seeing when we break up that hydrogen light, that pretty purple glow? Well, hold on. Let's go back and look at it again. So when we light up the hydrogen, when we have it glowing, and we split that light into specific wavelengths, we get these specific wavelengths. Okay, well great, we've got this. So we get a bunch of specific wavelengths. Every form of light, every color of light is moving at the same speed. It's all moving at c. Okay? Speed of light. Anybody know the speed of light? Anybody happen to have run across that at some point? Really, really fast. 3 times 10 to the 8th meters per second. Really, really fast. It's the speed limit, like permanently, universally. You can't go faster than that. Nothing can travel faster than light. This is what we think, which gets us into all kinds of problems with quantum entanglement and physics, but you won't get to that for a long time. Okay, so we've got speed of light, and we now have a wavelength. So we've got C, we've got delta V. Can we find the frequency of those lights that we're seeing? Yeah. 3-part algebra. Woohoo! Go us. You can all do 3-part algebra. So, for every one of those little bands of light you're seeing for hydrogen, you can figure out its frequency. Great. Why do we care, Moser? Here's why. Woohoo! Planck. Remember Planck? There was something that a lot of you put into your presentations that I think probably none of you really had a grip on, but you probably will after this. Planck's constant. Do you remember running into information about Planck's constant? H. What the heck is H? Planck's constant. Who cares? Well, there's an equation, and it's given in your lab packet. Energy is equal to Planck's constant times frequency. So for any one of those little bands of light that, remember, has a known wavelength, and we have a known C, we can figure out V. And if we can figure out V, then we can figure out how much energy that band of light is carrying, right? You could actually do, in physics, if you take physics, we do a lot of what are called substitution problems. So we could solve this equation for V. We would get C divided by lambda equals V. Then we can plug that in for V, and we end up with E equals HC over lambda. So we don't even ever have to handle the number for frequency. Okay, great. Still don't care, Moser. Anybody know what that is? It's a hydrogen atom. Yeah, single proton, single electron. No neutrons. One is the loneliest number. Something, something, something. I forget how it goes. What Bohr was saying, the reason that the hydrogen emission spectrum actually fits better with Bohr is that what he was saying is, hey, you know what? There is some mythical second floor. This is like an apartment building. And when we add energy to this atom, the electron gets booted up to the second floor. This was you guys going from standing on the ground to standing on your desks. Well, then that electron eventually is going to fall back down. And when it does, it gives off energy, a little quantum of energy, a quanta. And that quanta of energy is a very specific amount. Well, remember we were able to figure out E. It's equal to H times C over lambda. He was actually able to figure out that the energy he was seeing, those little wavelengths of light, add them all up, add the energy from all of those, he figured, well, hey, that's the amount of energy between this energy level and that energy level. He was using the hydrogen line emission spectra to get at something about the hydrogen atom. And it's pretty handy. Now, of course, we know, hindsight being 2020, that this didn't work for anything but hydrogen, not well. But this is where it fits in. And it is by far the hardest concept to understand, I think, in history of atomic structure. So I think most of you are still a little bit fuzzy on it, and that's okay. I don't expect you to have like a particle physicist's grasp on it. You're juniors and seniors in high school. It's taken me years of teaching it to understand it as well as I do currently, and I'm still not a particle physicist, nor will I ever be. But this is really the thing that triggers Bohr's model, is this hydrogen line emission spectra. He thinks he can explain it because of this relationship and the light that's emitted. So with the use of a prism, you can distinguish the different colors. Tomorrow we start Chapter 4 notes. This is the other part of Chapter 4, the part that you didn't already read in doing your atomic history stuff. Those notes will be up online. If they're not already there, they'll be up by the end of the day. And we're going to keep talking about energy levels. Okay? It's all related. It's a ladder you're building. Okay, you've got time to work.